Now that we've had some experience with arithmetic sequences and with geometric sequences, I'd like to take a look at this word problem because raises an interesting question. George is taking a job with a starting salary of 20,000. I know that's not a lot of money. Remember, it's an old textbook. Find his salary during his fourth year on the job. Now, we're not looking for the sum of how much money he's made the first 4 years. Just want to know how much he's making on his fourth year. And if George has a choice, he can choose between an annual raise of $1,100 or a 5% raise. So let's ask George, or have George do the calculations to try to figure out which would be better. Should he take the 1100 or should he take the 5%? Well, if we calculate starting with the 1100, that becomes an arithmetic sequence. Remember, arithmetic sequence, we are adding the same number to each previous term to get its successive term. In this case, we're adding $1,100 to George's salary to get what his salary is the second year. Whatever that is, we're adding $1,100 to that to get his salary for the third year. Whatever that is, we're adding $1,100 to get his salary for the fourth year. So in this particular situation, the first term in our arithmetic sequence is how much money George makes the first year, or $20,000. The common difference, what we're adding to his salary each year, is $1,100. And there's the formula for a reminder. T sub n equals T sub 1 plus n minus 1 times d. In this case, we want to know his salary on the fourth year. So all the n's, we're going to substitute in 4 instead of the n's. We already said T sub 1, the first term, is 20,000, and the common difference is 1,100. So let's substitute those numbers in the formula. T sub 4, the amount of money George will make in his fourth year, is 20,000 plus 4 years minus 1 according to the formula, times 1,100. 4 minus 1 is 3. 3 times 1,100 is 3,300. We add that to the 20,000, and on the fourth year, if George has taken the annual raise of $1,100, his salary that fourth year is $23,300. But what about an annual raise of 5%, a percent? So we need to look at that as a geometric sequence. We are multiplying each year's salary by a number, that's our common ratio, to get the successive salary. So we know that that's a geometric sequence. The first term in that is still $20,000 because that's what he's starting with. Now, here's something I need to take a moment to explain. We are not going to use 5% for R. If we were using the compound interest formula that we learned in Chapter 10, that would be a good thing. We also still need to remember that percent is written as a decimal, 0.05. But what we need to keep in mind is that the common ratio is going to be 1.05. And the question is, why? Well, if S represents George's salary, the second year, we're going to take his original salary, 20,000. We're going to multiply that by 0.05 and add that to the original salary. So 1s plus 0.05s is 1.05s. 1.05 is our common ratio. Now, just for the sake of argument, if for some reason you thought, well, it needs to be 0.05, let's try this out. Let's put in 20,000 and let's multiply that by 0.05, see what we get, and we get $1,000. So actually the first year, George's raise is $1,000, not $1,100. But if we use the common ratio as 0.05, watch what happens next. We are going to multiply that times 0.05, and then we find out that George in his third year, and if you get confused, you might think, wow, is he only making $50? Or is his raise only $50? So that's not going to do the trick. The 0.05 is actually going to make his salary his raise, well, his raise actually, decrease as time goes on. So we need to include the original salary plus the raise for each term in this particular sequence. So let's again remind you of the formula. T sub n equals T sub 1 times r to the n minus 1 power. We are looking for the fourth year, so we're going to replace all the n's with 4. T sub 1 we said is $20,000, and we're going to use 1.05 as the common ratio, again because it's its salary plus his 5% raise that we're multiplying each previous year's salary by to get the next year's salary. 4 minus 1 and our exponent is 3, and then we need to take our any base to any power button on our calculator and raise 1.05 to the third power. If we do that, let's take that 1.05. Here's on my computer's calculator, any base to any power button. Raise that to the third power. And then since we all want to get the same answer, let's just continue with the practice we started in chapter 10, and that's round this off to 4 places. So instead of 1.57625, 4 decimal places is going to be 1.1576. And then the last step of the process is that we multiply 1.1576 times $20,000, and George would be making $23,152 his fourth year if he took the 5% raise instead of the $1,100. Now, some of you are tempted to answer this question and say, well, George should definitely take the $1,100 every year, because certainly it makes a difference in his salary the fourth year, and it looks like he's losing money each of those years through the fourth year. But before we jump to any conclusions, I'm going to leave this as a solution for you to work on, but I'm going to raise this question. What if we have the same situation, starting salary of $20,000, he's got a choice of an annual increase of $1,100 or 5%, but George decides he's going to stay on this job over the long term. He wants to be there for 20 years or more. And I'm going to leave this as an exercise for the viewer. Calculate what his salary would be the 20th year if he took $1,100 raises every year or 5%, and determine whether the $1,100 would be better or the 5% would be better. And we'll be doing this in class if you're in class and have that answer. But here's the calculations you can refer to when we look at the 1100 as an arithmetic sequence and the 5% as a geometric sequence. The only difference here is you're going to replace n with 20 instead of 4 in both situations. So I look forward to figuring out if you decided whether the 1100 is better or the 5% is better by the time George is there for 20 years.